Hello, everybody. I hope everybody's doing well. I'm exhausted. Does anybody have any questions? Today, we're going to do a number of things. We're going to do molar reaction quantities. In other words, we're going to learn how to get thermodynamics from cells. We're going to do the Nernst equation, which I think most people remember. We're going to figure out how to evaluate standard cell potentials, because standard cell potentials are hypothetical, and they're hypothetical because of the standard state thing, right? The standard state is usually hypothetical. And then we're going to do standard electrode potentials, in other words, half cells. Most of this is discussed pretty well, at least twice in your previous life in chemistry. And we're just going to add a little bit of rigor to that, but it should be very familiar. So this seems like kind of an appropriate close to chapter 14 and DeVoe, especially today, as it looks like the election week is coming to a close. A lot of things are coming to an end right now. It's kind of funny how that happens. But questions? Nobody has a question? The other thing I wanted to mention, I guess, that I should have mentioned is the problem set 7 key is coming. I'm almost done with it. I just have like probably 10 minutes worth of work to do on it. And then the grading on that will also come probably today. So you can examine that. I don't have the feeling it was too horrible, but sometimes I'm surprised. So, all right. All right, so the first thing we're going to talk about today is molar reaction quantities. Okay, so in other words, we're going to deal with the reaction Gibbs free energy of a cell, right? This is a definition of the electrochemical cell. We could also think about a standard delta G, which pertains to the direct reaction. Now, remember what the difference here is. The cell is where we have the reactants and products separated, right? Either completely physically or by a barrier that's going to give a junction potential or something. And the direct reaction is where we just throw everything in the same beaker, right? And what we want to do is we want to compare and contrast these two things. And we're going to take the definition here That's pretty standard and goes with our earlier definitions just as pertaining to the cell. And this sum would be over the things in the cell, right? Because that summation is kind of non-specific. So we have to make sure that we know what we're dealing with here. So let's relate the delta G of the cell to the EMF of the cell. So what we want to realize is when both electrodes, remember that when we say electrode, it's probably what you think of as being the half reaction or the half cell. When both electrodes are at equilibrium, the reactions are also at equilibrium that are involved there. And if we recall that we use this letter Z for the stoichiometric number, usually we think about this as the number of electrons in the reaction, but we want to be a little bit more specific for that. Let's now make the definition where I alluded to this a second ago, how the summation is non-specific. Let's try to make this labeling a little bit more specific. So I'm going to use the I label for the left-hand electrode, and LE means the left electrode. On the right-hand side, I'm going to use a J label, just so we can differentiate these if we want to. And then on the left-hand side, we're giving up electrons. So we're gaining electrons. So we have a plus term for the electron potential. For the right cell, that's kind of the product cell, right? And in that cell, we're using up the electrons, so we subtract off the electronic chemical potential term. And at equilibrium, remember the definition is that this equals 0 at equilibrium. So what we're going to do is we're going to put these two together. And now you can see why I'm going to use different summation labels so we don't conflate them. And I'm just going to collect the electronic chemical potential terms. This all equals 0. And hold on, let me do it this way. This equals 0. Now what we have here, this first summation, each of those summations is the free energy of the reactants and the products. So those two together are the reaction Gibbs free energy for the cell, right? And what we can do is now we can make the electronic part, subtract that from the other side so we can equate the two. And of course, this changes the sign. This should be LE, not LF. And remember that LE means left electrode, RE means right electrode. Now, you know, DeVoe is very careful and kind of anal about each step, even for a physical chemist. So you start off talking about the electrode, But what we're going to do here basically he starts off just talking about the electrode. Then he's going to say that, well, we actually want to think about the terminal. In order to do the potential of the whole cell, you have to include the terminal, the wire, right? He's going to talk a little bit about how the wire, if it's the same on both sides, then you can make this encapsulation, and then this is going to enable you to get the cell EMF, the difference in potential from the both sides. This is kind of, as we would say, an academic discussion, right? It's a distinction without a difference, and it's something we normally don't talk about. So when he makes this jump from talking about the electrode to the terminal, this is just at a level that we usually don't even consider, right? We just consider the whole left or right hand side, the electrode / terminal, the same thing. So I would say that this is like a strict accounting, right? That's maybe the way you can explain a lot of the things DeVoe does, is a strict accounting. What we end up with is, on the right hand side, the free energy change of the cell. And what this enables us to do when we talk about the whole half cell on each side is we really have then the potential of the left, of the right, minus the potential of the left. And that potential difference we're going to define as the cell EMF. Now, one thing we haven't done here, I want to point out, because sometimes when we're kind of down in the weeds of looking at these equations and equating things and getting simplified expressions and so on, we don't think about what this means. We have not defined, and when I say defined, I mean in terms of the values of these things, right? In other words, we've conceptually defined these things, but what we're going to do, right, is now encapsulate those in the EMF of the cell. We're going to retain this conceptualization because at the very end, it's going to allow us to define the half reactions, the reduction potentials, and so on, right? But at this point, we really don't have these specifically defined, only conceptually defined. And I think that's important to think about right now. It's okay, there's nothing wrong with that, right? So the take home from this section is just this. And this is what we would think about in, say, Chem 25. We would have expressed it like this: the free energy change of the process equals minus NFE cell, right? So we're using Z instead of N, but that's all we're doing, right? So that should be familiar to you. Let's now think about the relation between the cell and the direct. Now, when DeVoe writes the delta RG, he doesn't put direct in parentheses, but that's what we're talking about. So in other words, we're comparing just kind of a reaction in a beaker to a cell reaction. What's the difference between the free energy change we might measure if we just have everything mixed in a beaker versus the cell? there should be some relationship there. It may or may not be the same. So what we're going to do is we're going to compare a cell setup. And we have to think of a cell. So let's think about the Daniel cell, which is in figure 14.2, for example. So we're going to compare this cell with a direct reaction. And for the species in a Daniel cell, this would be zinc, copper, like you could just put some zinc, what do they call it? Mossy zinc, you know, those funny zinc pellets, mossy zinc and a copper plate and zinc sulfate solution and copper sulfate solution all in the same beaker. And we're going to make sure the temperature and pressure of these two things is the same, right? So the question is, are these two things the same? And again, I'm going to slap on a direct label on the free energy of the direct reaction, just so we know what we're talking about. Now we're going to use our convention again, but now I'm going to put the J label on the direct side, right? This is really what we're asking. Are these two summations equal? Well, the thing is here that the stoichiometric coefficients are the same right? In other words, the reactions look the same. The coefficients of the two reactions are going to be the same. But the problem is the chemical potentials are not the same, at least for charged species, right? So in other words, because I create this cell and I separate the two sides, we know this creates an electromotive force, or basically an electric field through the two sides. And in the first case, where we just have everything in a beaker, it's a uniform system. So there's no electric field going on, right? What we've basically done is we've broken down this electric field going from one side to the other. It's not quite the same as like turning a summation into an integral, but it kind of is, right? Where all the little fields are happening on, let's say, an atomic or molecular level rather than this side to this side, right? So it's kind of like the difference between a gas doing work and a dropped weight doing work, right? So it's kind of similar to that. I haven't really seen this kind of entropic treatment, but I think it's kind of related to entropy, although I haven't quite figured that out yet. But anyway, this means the charged species will have different chemical potentials in the two systems. So that gives us something to kind of focus on. So let's think about two cases. The first case, we're going to think about a cell with no junction, right? Or no junctions. The schematic for this would be like figure 14.1, right? Where we just have the two cells across the same solution from each other. Okay, in this case, when all the ions are in the same solution phase, the field between the two electrodes is uniform. So the thing I want you to think about here is, I think it's figure 14.3a. Do you remember where we had the junction potentials at each interface, and they're all horizontal or vertical, right? So across at each phase, the potential is uniform. The only thing where they change is there's a sudden drop at a junction. So what happens here is this is independent. This summation is independent of potentials. This we actually discussed this before. You probably it might be a little foggy in your memory, even though we did it yesterday or Monday. But in this case, the two are equal, right? Okay, now let's take another case. We have a cell with junctions, right? So now we're going to have a cell with junctions. In this case, we have this. Let's go ahead and put in the full kind of expression. This will look familiar with what we did last time. We have these free energy terms in the field, right? So this is what we have. Now we definitely have a field. In other words, we have a potential. We're going to have a break across a junction. Well, let's put what we have here. We have the zero field part, which looks like this. Right? And we have the field part, which looks like this. So I'm saying we have on either side of this junction, we have an alpha phase and a beta phase. They could both be aqueous, but they're considered to be unique. And again, you may want to look back on what we did on Monday to see where this comes from. All right, well, let's look at this. The first line here is really just the free energy change for the reaction, right? The second part is, we can call this minus ZF EJ, where this now is, we're going to call this the junction potential. EJ equals, or is defined as, the beta phase field minus the alpha phase field. Notice that we switch the order of these in order to introduce a minus sign. And the other thing to notice, and this is a little bit confusing at first light, is that now this J represents junction, and it's not our summation variable, okay? They're both J's, but we have a capital J that stands for junction and a little j, which is our summation variable. All right, so in other words, what we get is this. I'm sorry. These are two terms that we get, but remember, all this equals the cell free energy. So I have to write it like this. Okay. All right, so what we can do is we can solve for, we know that this, right, equals minus ZF E cell at equilibrium, right? That's the definition of the left-hand side. So, and if we make the same connection to the non-cell or the free or the direct reaction, right? We can say that minus ZF E cell equilibrium equals minus, oh, hold on. I'm thinking ahead to the Ks. So let me erase this ETC because that's not what we're going to do. I'm sorry. All right. So what we can do is we can solve for the equilibrium cell potential. Getting a little sloppy here. This is going to be minus delta G over ZF if there's no junction. If there is a junction, we just have to include a junction potential, right? And if we want to make this more simple, we can say that right? In other words, if we work in our experimental setup to make junction potentials 0, right? If they're small compared to everything else, then we can at least say, we can at least have this equality to a good approximation. And again, it might help to think about what we have here. In other words, now, I think, let me mention for a second, I think in freshman chemistry, we start by talking about standards, right? That's always our context. So we come at this, the first time we see an equation like this is that the standard cell potential equals the standard delta G over ZF. But we're not doing that here. We're just getting the general case. And what we're going to do is get the specific case later. Okay, so let's talk about standard molar reaction quantities. In other words, thermodynamic quantities. How can we get thermodynamic quantities from a cell? Okay, well, first of all, a standard cell, if we want to talk about a standard cell, standard states, has all reactants and products in their standard states, unit activity, and a negligible junction potential, right? So what this gives us is something we could call the standard cell potential, right? But what we have to realize, my pen's looking a little fat today. What's going on? I don't know if any of you use an Apple Pencil, but I keep forgetting that if it seems to be drawing fat all of a sudden, it's probably because it's not screwed in very well. Okay, so what we want to do is we want to realize that this is a hypothetical. Right? In other words, we could never hope to have unit activities in real life, right? We have the ideal dilute limit, we have Raoult's law limit, et cetera, et cetera, et cetera, right? So this is purely hypothetical. In freshman chemistry, we would say, oh, we just have 1 molar concentrations and 1 atmosphere of pressure. But at least when I teach this to freshmen, I'd tell them, well, even if you did this, right, even if you made a 1 molar concentration of everything and 1 atmosphere of pressures in a standard hydrogen cell or whatever, and you measured the voltage, you would not you would not get the cell voltage that you would find in a book. You just wouldn't, right? And now we know why, because it's standard states are really hypothetical states. All right, but within this hypothetical state, right? Within this hypothetical state, as long as we realize this is hypothetical, we could make this definition. And we could also say, because of the relationship between delta G standard and K, we can immediately make this connection. Okay, so what we can say at this point is we can say that these things are the standard cell potentials are some sort of goal that we have, right? Because if we can know those, then we can know these very important things, equilibrium constant and delta G naught. Because we've talked a lot about working with delta G naught and the equilibrium constant. We actually haven't talked a lot about working with the equilibrium constant, but we know that's important. But how do we figure it out? And it turns out electrochemical cells provide us a way to do this, but we have to work through a few details about how we do this exactly, because this is a hypothetical state. So let's see an example of this. So if we apply this to a cell that's similar to figure 14.1, remember figure 14.1 had a hydrogen electrode over here, and the silver chloride electrode over here. Let's do it a little bit different. Let's do a silver electrode, a plain silver electrode on the left, and a silver chloride electrode on the right. So that's going to look like this. We're going to have some sort of junction here. We're going to have chloride. We're going to have AgCl, and we want to say this is solid and silver. Right. So if you looked at this line notation, you should immediately recognize this will give you a potential, right? Because the two sides are not the same. If we break out the reactions, this is the left, right? Which is oxidation. This is, you always do this, right? You kind of do this check to make sure that everything is consistent, right? On the right-hand side, we have reduction. So we have this. But remember, we have this funny situation where we add the electron to the solid silver chloride, freeing up silver plus a chloride. Now, what's the net reaction? The net reaction is AgCl going to Ag plus Cl minus. You may recognize this as KSP AgCl. This is the KSP reaction for AgCl. So the idea here is could we get the cell potential and turn this into KSP? Well, let's assume assume a measurement. I'm putting this in quotes because it turns out not to be this easy, but let's assume a measurement gives negative 0.5770 volts. Now, as I said a couple minutes ago, it's not going to be as simple as setting up this cell, hooking up a voltmeter to it, and getting this voltage. That's not going to happen, right? So when I say assume a measurement, this is actually going to be a process, right? Like everything else we do in this, we're going to have to do some experiments, probably do some sort of plot and do an extrapolation, right? But anyway, let's assume that this is what we get out of all that work. And then we can say log of K equals F over RT times minus 0.577 volts. This happens to be, the value of this happens to be minus 22.46, right? And this gives the KSP for AGCL 1.76 times 10 to the minus 10. So I don't know if you remember the value of KSP for silver chloride, but over 25 years, I have this memorized, and the generic value of this is 1.8 times 10 to the minus 10, right? So if you look back in your Chem 25 textbook and look up the KSP, this is the value of KSP in the tables at 25 degrees C. So that's how you would do it. So at least theoretically, we have a method to do this. And the thing is this is the best way to determine KSPs. If you can generate a cell somehow that gives you the net equation, the net KSP equation that you're looking for, that may be a trick in and of itself, right? For the AGCL one, it gives us a couple of pretty familiar electrodes. But for other KSPs, I don't know. Could we do it? I don't know. Maybe. But this is the best way to get these values. It turns out it's very sensitive. Okay. All right. Once we open the floodgates here, due to our known relationships, between K, delta G, delta S, and so on, we could come up with expressions like this. This is one of the Van Hoff expressions, and we could turn this into a modified Van Hoff expression, which is really what we should call this. All right, so let's look at this. This is the equation of a line, right? So in other words, if we plot our cell voltage versus temperature, right, it gives us the reaction enthalpy, right? And the intercept is the standard cell potential. So now we're getting somewhere, right? This looks like we should be able to plot some data and get some of the things we want. Turns out it's still not quite this simple, but we're getting there, right? And by the way, we could get entropy. And so on. So we have these relationships that we can work with. All right. Now, but here's the trouble, right? And let me be a little bit more specific here. A little bit, bring this out. It looks like we can plot this, and the intercept is the standard, right? But what are we plotting here? According to this equation, we have to plot the standard cell potential versus temperature. And that's a hypothetical That's a hypothetical. So it turns out we can't really get this. We really can't just get this, right? So it's not as easy as it looks. So we still have a little bit more work to do. And for that, we need the Nernst equation. We need the concentration dependence of this voltage, right? Because now this is what we always do, right? We get the concentration dependence of some variable. And then if we extrapolate this to zero concentration or whatever concentration our standard is defined at, then we can get the standard cell potential. So that's why we're doing this. In order to do that, we relate Q and K and E cell to the standard E cell, right? So this is what we're going to do. It's not super difficult, especially since you've seen it before. We can say this. This is from our previous chapters in thermodynamics, right? If we turn this into the cells, we can say this. And this is the Nernst equation. Okay. And the only assumption here is that junction potentials are zero. And it turns out if you're a good experimentalist, you can usually get the junction potential just about a millivolt or something, right? So you can get it essentially zero. Let's talk about a dead cell, right? A dead battery. The cell potential is going to be zero. And additionally, the Q becomes K, right, in that circumstance. So what that gives us is that this standard cell potential is RT over ZF ln K. All right, so this looks promising, right? Because now all we have to do is use the value of the equilibrium constant in our standard state, and that can give us a standard cell potential. So this is a pathway to this hypothetical, right? There's a standard kind of substitution everybody makes. If you're at 298K, then RT over F is 25 millivolts, 26 millivolts. So what you get is this. You have to be careful though, of course, right? Because if you're not at 25 degrees C, it's going to change this a little bit. Right, you get that. So this is the Nernst equation at 25 degrees C. So how do we evaluate this? So now, like I said, we have the pathway. So let's see how we go about evaluating this standard cell potential. So as I said before, we cannot do this from a single measurement. We're going to have to do some sort of series of measurements and extrapolations. So let's take a specific example. This is going to be figure 14.1. This is a case where the junction potential by definition is zero. There's no junctions. We just have one solution across the whole thing. Here's the reaction. So there's the overall reaction, right? And in Chem 25 terms, we would say something like this, right? The Q is going to be H plus squared over chloride ions squared divided by pH2. So this is, of course, not the way we're going to write it in this class, right? This is too simplified, but I think it helps to write it the way we're used to seeing it, because then you can, make the connection to what you expect, right? So what happens when we write this all out? Well, we get a big long expression, and since we know how to do everything, activity coefficients and so on, right? So the first thing you might want to do is put this in terms of the real expression. And if you do that, it's going to look like this. And of course, what we're doing is we're gathering the powers into a prefix. So that factor of 2 comes from the activity coefficient squared, right? That's where that comes from. We're just going to use the molality of the solute rather than breaking it up into individual ions, because that seems a little bit easier. And we'll use the fugacity of H2, right? So we're using a molality basis and a fugacity basis for the gas. So we get something like this. And if you think about it, everything on the right-hand side is measurable, except for the activity coefficient. This is indirectly measurable, right? We've seen how we could get this value. What we're going to do here, we know that this mean ionic activity coefficient approaches 1 as the molality of the electrolyte approaches 0, right? Remember, this is why, remember on the test, I asked you for these limits, right? We should really know what these limits are, because maybe we want to take them to 1. We need to know when we're taking them to 1. That means the logarithm goes to 0, right? So in this limit, we can ignore that first term. I'm sorry, the second term, the mean ionic activity coefficient. Or if we wanted to be better, we could use Debye-Huckel law. To express that. Now, we know how to do this too. This makes for a kind of thicket of an equation, but again, it's doable. And so what we end up with is, we'll call it E prime of the cell, because this is kind of an approximation or a modified expression, right? It's not strictly, since we're inserting the Debye-Huckel law into this, which is in itself an approximation, we cannot truly call this the standard cell voltage anymore, right? What we're going to say is this approaches that, right? Okay, anyway, what does this look like? Well, we get the measured voltage, which is easy. And then we get the Debye-Huckel part. There's a 2 here. And it looks like this. And I want to be accurate here, but the point is that if you were actually going to do this, then you would look that up, see what it was exactly, right? Now, if you're at constant pressure, in other words, if your standard hydrogen cell, if you have a regulated constant pressure in that cell, that's actually pretty easy to attain, then that last thing goes to a constant, right? So now we're left with two terms, and really what we have is we have a kind of complicated expression in M, but we know, right? We know in the limit as the molality goes to 0, this will go to a constant value. So what we can say is this value that we plot or whatever is going to approach the standard cell potential, right? And the better our expression is, the better that extrapolation is going to be. And I don't know if I copied this figure. I should have, because there's a let me look really quickly. I think I did. Yeah, so let me show that. So this is this is just from your book. You've probably seen this before, but look how noisy the data is, right? And this is taking your measured cell voltage, but then you put it into that equation, right? And you plot it, and you just do as many measurements as possible. So even though this data is really noisy, look at the scale. So the bottom of the scale, the difference between the top of the scale and the bottom of the scale is 1 millivolt, right? So, and the molalities are very dilute, right? So this is kind of a pain to do this. You do just think of all that would go into this careful experiment, right? But you get a pretty good value. I think the value you get from this particular set of data agrees to like the tabulated data to within like 0.5%. So it's pretty good agreement, that which tells me that the data is truly shows random errors, right? It's above and below. Anyway, this is how you would do it, but each of these points comes from that equation. Each of these points comes from that equation here. And this is a example of where the whole expression, the extrapolation is the whole expression, and the whole expression approaches the value you're looking for, rather than identifying the intercept as one term in your linear expansion. Okay. Let's now talk about standard electrode potentials. And really what we're going to do here is we're going to use Hess's law to be able to get some useful information. And this is another case in DeVoe where DeVoe does not talk a lot about the import of, say, standard reduction potentials. A standard reduction potential table kind of speaks for itself, right? We use it for a lot of things. So the idea here is not trumpeting how important these values are or what the table is. It's more like, how do we get these things theoretically, right? So we've all seen and used standard reduction potentials, right? And so let's examine how we arrive. Okay. In order to do this with any other kind of thermodynamic state quantity, we must define some electrode, or let's say not electrode, terminal is the correct term. Right, we have to have some frame of reference. And that electrode is the standard hydrogen electrode. So when I was a student, when I was an undergraduate student, the electrode that was in books was the calomel electrode, which is a mercury electrode, a saturated mercury electrode. Even though at that point, they had moved on from the calomel electrode to a different electrode, which I don't even remember what it is. And then sometime during that time, they were moving to the standard hydrogen electrode as the standard. And each of these electrodes differs in its half voltage by a millivolt or two. So it turns out that if I found one of my old textbooks when I was an undergraduate, it's probably in my mom's basement or something, right? Then those, the half voltages that would be in that book would be different than what we see now, just by a little bit, right? And this is still a hypothetical electrode, right? Because it deals with standard states, so it's going to be a hypothetical electrode. But if we combine the standard hydrogen electrode with other electrodes, of course, we may define or use the electrode potential. Which is really just half a complete EMF. Okay, so how do we do this? What if we are given a standard hydrogen electrode, an electrode 1, which we're going to call EL for left, another electrode, which we're going to define as ER for the right. And the only reason we're going to do that is that in cell 1, we're going to use those two electrodes together, and we're going to put one on the left and two on the right. Right, so we're going to use those two electrodes, and we're going to measure the voltage, which is itself a large task. This might take us like 6 weeks, right? Okay, and in cell 2, we're going to have a standard hydrogen electrode, which is going to be on the left side, okay? And then we're going to put the left electrode, the way we defined it before, on the right side. What this is going to give us is this E cell is going to be defined then as the standard potential of the left-hand cell. Because we define this, the hydrogen electrode as E0, recall this, right? So this is where we're going to use that theoretical definition before, and each of these then we could call this little phi, right? Because this, the way we define this is generally true for any cell. We just haven't figured out how to measure these yet. Here's how to do it. Okay, cell 3, we're going to have the standard hydrogen electrode on the left, and this cell we've labeled E right on the right. And in this case, the cell potential is going to be E right. Okay, or Phi right, however you want to call it. Now, how do we know this? Well, we know that the right hand cell is reduction, the left hand cell is oxidation. And again, I'm going through this again. DeVoe doesn't do this. DeVoe doesn't go through this again, but I think it's important to kind of center what we know. When we're learning new things, it's important to center with what we know. And we know this kind of thing, right? So this would be something like the copper 2 plus 2 electrons going to copper, for example. This would be something like the zinc going to zinc ion plus 2 electrons. In other words, this is the reactant, this is the product side, and so on. So all this kind of definition is consistent, and we should be able to use that kind of handhold in our reality to understand this. Because when you give this right hand voltage minus left hand voltage to freshmen, it's confusing, right? It just seems like it's a black box equation. It doesn't come from everything. But now we can kind of understand where this comes from. Okay. To do this, we really use Hess's law. What do we say? We say the free energy of reaction 1 plus the free energy of reaction 2 is going to be the free energy of reaction 3. You should see this. This is true by additivity, right? If you add the reactions together. I'm kind of mixing my labeling a little bit, but I hope it's obvious what I'm doing here. In other words, now the way we've defined these, if you look up at the top, then the first reaction we're just going to call E cell that we want for the first reaction. This is right. So that's where this comes from. Now, what's important to realize, and this is mentioned in some freshman textbooks, but it's usually not with electrochemistry. It's usually, there's usually in freshman chemistry, there's like a survey chapter where they devote a whole chapter to kind of like a little bit more detailed chemistry of the elements or the groups. And one of the things that's usually buried in there are a relative reduction potentials of an elemental series. In other words, if you have an element that can exist in many different oxidation states, let's just think manganese, right? Manganese has like 4,200 oxidation states, really only 7, but it's a lot of them, right? And so what you do is you can write down all the oxidation states and the form that these are in, like permanganate and MnO2 and MnO and everything, right? You write these down, and then you draw lines connecting them with voltages, standard reduction potentials to get between them. But the way you have to find those values is using this Hess's law formulation. So and it's worth mentioning because I don't see DeVoe mentioning it, and it is important. So this is an example of where you have let's say you have iron 2 plus 2 electrons goes to iron. Iron 3 plus 3 electrons goes to iron. And then you have iron 3 plus an electron goes to iron 2. Well, this is a case where if you're given these 3 half reaction voltages, you can't add the voltages as if they were free energies, right? So if you look at these 3 reactions, 1, 2, and 3, there's a Hess's law problem on the problem set that you turned in last week, right? So if you look at the key, you'll see the way I'm writing this. In terms of delta H, if we wanted to find the delta H of these reactions, if you look here, you can see that if I reverse the first reaction and add it to the second reaction, I get the third reaction. In other words, 2 minus 1 equals 3. In other words, delta H2 minus delta H1 equals delta H3. And that's what we did up here. That's how we started this, right? But the difference is when we convert these to cell potentials, we have this factor of ZFE. The trouble here is that here, the Z equals 2, here the Z equals 3, and here the Z equals 1. What we did above is all the Z's are the same, so we cancel them. And that's not really apparent in when you do that treatment. It's not really apparent that all the Z's are 1. Or I'm sorry, in fact, they're 2 up there. But since they're all the same, you cancel them. You can't do that here, right? So the way we would do it here is if we want this, knowing the other 2, you can't just do a straight add, right? You have to say, well, delta G minus delta G1 plus delta G2 equals delta G3 to get those pluses and minuses. And maybe stoichiometry, you have to set up a Hess's law type problem, right? And then what you have to do is this. Actually, let me be careful here, right? Minus, well, the first reaction has 2, right? The second reaction has 3. The third reaction has a factor of 1. I'm putting this in red just so you can see it, obviously. So if we want E03, the F's all cancel, right? Clearly the Faraday factors all cancel, but what we get is this is going to be 3 E02 minus 2 E01, right? In other words, it's not linear. Very often you do this where the reduction that you want has 2 or 3 or 4 electrons, and the equations you put together have 1 or 2 electrons. So you have to be careful what you have to divide by, right? So here I'm technically dividing everything by 1F, right? And that cancels the F's everywhere, right? So you have to be careful. And electrochemistry is so useful, and sometimes you want a reduction that that's not necessarily tabulated, and you need to know how to get it, right? There is a way to get it through the state functions, but it's not obvious. Okay, that's it. That's chapter 14. And that's the end of the green book. That's the end of the DeVoe book. So Over the weekend, I'm sure you'll be maybe working on the problem set and preparing for the exam. After that, come Tuesday, we'll have I'll put up the text that we'll use, PDFs of the text that we'll use, so it'll be easier for you to find, including kinetic molecular theory in case you want to review that. Like I said, there's going to be actually large swaths of that chapter that I don't even want you to consider. So I'm only going to publish the parts that I want you to look at, so there's no confusion, and so you don't feel like the very difficult stuff at the end is important. But if you have any questions or any problems with that, please let me know. I will be around. Oh, I see a chat. Uh-oh, I hope something wasn't going wrong. Oh, sorry. Have a good weekend. I hope everything's going well. Just let me know if you need my